Of all the substances involved in the chemistry of life, there's no doubt that the most versatile are the proteins. The key to this versatility is the immense variety of molecular structures possible in proteins. Protein molecules consist of one or more chains made up of amino acid units, each of which can be any one of the 20 or so naturally occurring amino acids, resulting in almost unlimited variation. Proteins play a crucial role in virtually all biological processes. For example, they're the main component of muscle. There are transport proteins such as hemoglobin, which conveys oxygen in the bloodstream. Enzymes are specific proteins which catalyze the many reactions involved in living processes. And proteins are also one source of an important group of substances called peptide hormones. Peptide hormones are involved in the regulation of many vital processes in the body. In this program, we shall look at the role of one such hormone called LHRH, and how, by understanding the mode of action, it proved possible to develop a drug that mimics the action of LHRH. LHRH stands for luteinizing hormone releasing hormone, and that's exactly what it does. LHRH is produced in the region of the brain called the hypothalamus. Its function is to act as a kind of messenger by travelling to the pituitary gland at the base of the brain and causing the release of two other hormones called luteinizing hormone, or LH, and follicle-stimulating hormone, FSH. These two hormones are then transported in the bloodstream to the ovaries or testes depending on the sex of the individual. In the female, this stimulates the production of yet another hormone, the steroid called estrogen, often called the female sex hormone. In the male, it causes the release of the male sex hormone, another steroid called testosterone. In healthy people, these steroids are of course necessary for a variety of reasons, not least of which is the bearing of children. But suppose the action of LHRH could be blocked in some way, say by the use of a drug. This would prevent the production of the male or female sex hormones, and the result would be a powerful method of contraception. Alternatively, since testosterone and estrogen are necessary in cases of prostate or ovarian cancer to allow the tumour to grow, the same drug could be used as an anti-cancer agent. In the second half of the programme, we shall be looking at the scientific background to the development of just such a drug, one that is being marketed for the treatment of prostate cancer. One of the first steps in the development of a drug like this is to find out how the natural hormone works. Since such minute amounts are present in the body, the only way such studies can be carried out is to synthesize the compound in the laboratory. How then would we set about making LHRH? This is the formula of LHRH. It's a decapeptide. That is, it contains 10 amino acid residues. It looks very complicated, but we can simplify it greatly by using a shorthand for the individual residues like this. The best way to synthesize a peptide like this is to use the solid phase method. This involves the use of a polymeric support with a large number of chemically reactive groups. In principle, the first amino acid can then be attached to the support by a chemical reaction. There are two things to note about this process. First, the amino group has to be protected to prevent unwanted side reactions. And second, it turns out that in practice, better yields are obtained if the first amino acid is attached to the polymer by means of a linker group. Since the end product at the carboxyl end of LHRH is an amide group, it's most convenient to use this methyl benzhydrylamine group to link the growing peptide to the polymeric support. On acid hydrolysis, this cleaves to give an amide group directly. From this point on, each successive amino acid unit is attached in the same way. First, the protecting group on the N-terminus of the resin-bound peptide is removed. Then, the incoming protected amino acid is activated. followed by reaction with the free amino group of the peptide segment attached to the resin. Once reaction is complete, the protecting group is cleaved, and the cycle is repeated for the next amino acid in the sequence. Such a repetitive process is ideal for automation. We've come to the laboratories of Applied Biosystems here in Warrington to see how such a synthesis is carried out in practice using a peptide synthesizer. This instrument is a highly sophisticated microprocessor-controlled peptide synthesizer. You can think of it as probably the most versatile cocktail mixer in the world. The heart of the control system is this built-in computer. The first thing we need to do in synthesizing LHRH is to program in the amino acid sequence. This is easily done using this touchscreen display. First, we need the peptide sequence editor. Then we have to enter the sequence beginning from the N-terminus. The first amino acid, pyroglutamic acid, is slightly unusual and is stored under sp1. Then comes histidine, tryptophan, serine, tyrosine, glycine, leucine, arginine, proline, and finally another glycine. And there we have the complete LHRH sequence on the screen. We then need to tell the computer that the C-terminus is an amide. And finally, I'll store the sequence. We'll call it LHRH. The next step is to load the instrument with the protected amino acids in the correct order. Each amino acid is supplied in one of these small cartridges. On the back is a barcode so that the instrument can check at each stage that the correct amino acid has been loaded. We've already put the 10 amino acids in order, so I'll just load them in. To dispense the amino acid, 2 needles are injected through the rubber cap at the top of the cartridge. These are used to inject the solvent to dissolve the amino acid, and for nitrogen, first to agitate the solution, then to transfer it to the activation vessel. Once empty, the cartridge is discarded. Each amino acid in turn is dissolved in dichloromethane and then transferred to an activation vessel. Rather like a domestic washing machine, the instrument has a number of possible programs, depending on the particular amino acid to be activated. Most amino acids are activated by reaction with DCC, which converts the amino acid to a symmetrical anhydride. There are a few exceptions to this, one of which is arginine. The symmetrical anhydride of arginine is too unstable to use, so instead the amino acid is converted to an activated ester using hydroxybenzotriazole, or HOBT for short, again using DCC. After the byproducts have been filtered off, the resulting solution of activated amino acid is then automatically transferred to the concentration vessel. Here, the dichloromethane is removed and replaced with a smaller amount of dimethylformamide, DMF, which is a more polar solvent. This is necessary for maximum efficiency of the coupling reaction. The activated amino acid is then transferred from the concentrator to the reaction vessel, where it's allowed to react with the resin for about 20 to 30 minutes. After the excess amino acid has been washed away, the resin-bound peptide chain is treated with trifluoroacetic acid, or TFA for short, to remove the N-terminal protecting group, and it's ready for the next cycle. This is the activation vessel, where the amino acids and the coupling reagent are reacted together. When complete, the solution is transferred automatically to the concentration vessel. There are 3 reaction vessels so that the machine can be programmed to synthesize 3 different peptides completely automatically, one after the other. For our synthesis, we shall only need to use this one. It's here that the resin-bound peptide is deprotected, neutralized and washed prior to coupling with each activated amino acid. Of course, all the components of the delivery system are made of inert materials, and thorough washing of all surfaces is carried out after each step to wash away reagents and byproducts, so as to prevent any possibility of cross-contamination. The reagents are stored here. This is the base used to neutralize the solution after treatment with the trifluoroacetic acid, which is in the next bottle. Then over here, this is the methanol used for washing. And here are the bottles containing the 1-hydroxybenzotriazole and the DCC. These large bottles contain dichloromethane and dimethylformamide. At the bottom are 4 empty bottles to receive the waste solutions as the synthesis proceeds. To start the synthesis, we just need to press the Begin Synthesis key. The synthesis will then proceed entirely automatically until completion. The synthesis is now virtually complete. In total, it's taken less than 20 hours to reach this stage. In the reaction vessel is the completed decapeptide sequence attached to the resin. For the final step, it's necessary to move to what is known as a wet lab. All that remains to be done is to cleave the peptide from the resin and remove the remaining protecting groups. The resin is first stirred for several minutes with a mixture of compounds which help to minimize side reactions during hydrolysis. One cubic centimetre of trifluoroacetic acid is then added, and the resin equilibrated for 5 to 10 minutes. About 100 microlitres of trifluoromethane sulfonic acid is added to the flask, now immersed in an ice bath, and the mixture allowed to react for a further 25 minutes. The resin is filtered off, and the filtrate passes into excess ice-cold ether, where the liberated peptide precipitates. Finally, a check of the purity of the product has to be made using high-performance liquid chromatography. The results show the product to be about 85% pure. Allowing for losses at the cleavage stage, this indicates that each of the 10 stages in the synthesis must have been, on average, better than 99% efficient, a remarkably high value, yet one that is routine in solid-phase peptide synthesis. By using a larger column and different conditions, HPLC can be used not only as an analytical technique to determine purity, but also preparatively to isolate pure product. Indeed, such is the power of HPLC to separate even closely similar compounds on a large scale that its introduction can be said to have revolutionized peptide synthesis. So, Here is our sample of LHRH, available for study in a program for the development of LHRH agonists or antagonists. That is, drugs that mimic the activity of LHRH in the body or that block its action. Such a synthetic program of investigation was instigated by ICI Pharmaceuticals here at Alderley Park in Cheshire some 15 years ago. The problem with using natural peptides as drugs is that they're very unstable in the body, so that they're usually metabolized long before they reach the site of interest. That's why LHRH itself could not be used as a drug. How then did the ICI scientists set about searching for LHRH analogues? Dr. Anand Dutta, group leader here at ICI Pharmaceuticals, takes up the story.
The main objective of the project was to discover and develop a new drug which could be useful for the treatment of hormone-dependent tumors. The parent hormone LHRH had been discovered in round about the same time, and this gave a chance to develop compounds which can actually act at the pituitary level, and by working at that level they can actually desensitize the pituitary receptors if given in continuous and large enough dose levels. And by doing that, they can actually block the release of steroidal hormones, which are necessary for the growth of certain forms of cancers.
LHRH has 10 amino acid residues. Are all 10 necessary for optimum biological activity?
Some of these residues can be replaced, but in terms of shortening the peptide structure, one can only shorten it by one amino acid residue, and these 9 of those appear to be essential for the biological activity. That C-terminal glycine residue can be replaced, but the resulting nonapeptide is only 10% as potent as LHRH itself.
What directed you to the particular parts of the LHRH molecule that you decided to modify?
The main objective was to actually prepare compounds which were much more potent than LHRH, and because of that we attempted to modify a number of positions. But the two main ones which we concentrated upon were positions 6 and 10, and there were two main reasons for that. One of them is the enzymic stability of these peptides, and at that time there was some information available which indicated that peptide bonds formed by these two glycine residues may be more susceptible. The second was a conformational reason, which is glycine being one of those amino acids which does not have any bulky side chain, actually allows a large number of conformational possibilities. And therefore, if one can restrict some of those possibilities, one can achieve a conformation which is more suitable to the receptor. And by carrying out those kind of changes, it's possible to get compounds which are much more potent than the parent peptide, and at the same time much more stable than the parent peptide, and therefore are likely to be longer duration of action.
What led you to incorporate an amino acid with the unnatural configuration into the molecule?
Again, for the two main reasons, which is the conformation and the stability. One of the methods which is used for preventing the degradation of peptides is to use unnatural amino acids, because in the natural system where the enzymes are able to cleave the L-amino acid residues, they are not able to cleave the peptide bonds formed by the D-amino acid residues. So that was one reason for putting it in there, and the second reason was because by putting D-amino acid residues, especially the ones which have a bulkier side chain, for example, leucine, tryptophan, and tertiary butylserine, these, by the bulk of the side chain, they cut down the available conformations very significantly. And there is always a chance that by cutting those down, you are able to concentrate on a conformation which is more suitable for the receptor.
What caused you to use an ASA amino acid to replace the terminal glycine residue?
ASA amino acids are the residues which have the alpha CH of an amino acid replaced by a nitrogen. And this replacement leads to two effects. One is it can restrict the conformation very significantly, and at the same time, because these unnatural ASA residues are not recognized by the enzymes, the peptide bonds formed by these residues are also much more stable.
Once you decided on the target molecules you wanted to synthesize, what determined your synthetic strategy?
In this kind of a program, one of the main objectives is to make a reasonable number of analogs, and therefore the route would have to be good enough to provide you those larger number of analogs with minimum amount of synthetic effort. With that aim, we considered both the procedures, the solid phase peptide synthesis and the solution methods of peptide synthesis. And at that stage, we considered that if we can divide the molecule into 3 parts, which we did in terms of dividing it into the N-terminal tetrapeptide and the middle tripeptide and the C-terminal tripeptide. Then, say for example, if we were modifying position 10, then we only need to make the C-terminal tripeptide, and we can use the other fragments which were available before. And in this way, for each single analog, it's only that single fragment which needs to be synthesized. The other main reason was because most of the analogs which we were making had an ASA residue in position 10. And although the methods are available and ASA peptides can actually be made by using solid phase synthesis, but it's not very convenient at present to synthesize peptides which have a C-terminal ASA residue by a solid phase method.
What method of purification did you use for the various intermediates and the final product?
All the fragments were purified by column chromatography. The final products were purified either by column chromatography using Cephadex kind of materials or by using a countercurrent distribution method. Some of the analogs were also purified by using HPLC.
Given the tendency of peptides to be readily metabolized, how is the drug that you finally developed administered?
One of the main problems with peptides is that although they show activity when administered by various routes, which is orally or intravenous or subcutaneously, but the absorption from those sites is actually very small, and therefore huge quantities are required to be administered to see a desired biological response. So for that reason, we developed a formulation in which the drug is actually dispersed into a polymer, and using that formulation, only about 3.6 milligrams of the peptide could be administered, and the effect of that then lasts for at least 28 days. So therefore, it's only necessary to inject once a month.
The drug that ICI developed, gozerelin, is one of an increasingly large number of drugs based on peptides that are now available or currently under development. With the literally millions of possible sequences of amino acid residues, the scope for the development of precisely tailor-made therapeutic agents seems virtually unlimited. With the ever-increasing realization of the importance of peptides in the body and the possibility of scaling up solid-phase peptide synthesizers to production size, there seems little doubt that the peptide chemist will play an increasingly important role in the development of the drugs of the future.